All right. Hi and welcome, everyone. My name is Martin Schuetz. I originally come from Munich. I live in New York these days, so it's great to be back. Thanks to Robert and the organizers for having me and putting together this terrific program. So I'm the global practice lead for the Amazon Advanced Solutions Lab. I'm going to try to give you a broad overview of how we think about quantum computing at Amazon. But then I also want to dive deeper and give you a little bit of technical details, focusing on recent work together with JP Chase, where we developed a new algorithm called Q-Redomis, quantum-informed reduction algorithm for the maximum independent set problem. All right, let's get started. This is how I want to break this down today, give you a broad introduction about quantum computing at Amazon. Want to then, on a high level, describe the challenge, the situation that we faced when we started our collaboration, in particular with JP Chase, one of the largest banks in the world, and then pinpoint on a high level the solution that we came up with that is focused on the maximum independent set problem and how you can solve it, in particular with Rydberg atom arrays. We want to then dive deep into this algorithm called Q-Redomis. We're going to test it, we're going to assess the performance of this algorithm, and then we're going to conclude with a summary and an outlook. Okay, so this is what quantum computing looks like on a high level at Amazon. Essentially, we have three major teams from left to right. First, there's Amazon Braket. That is our service for quantum computing. So if you log into the AWS cloud today, you can have access to state-of-the-art simulators and different quantum backends, trapped ions, neutral atoms, superconducting qubits, all delivered to you within one unified user experience through Amazon Braket. The second pillar is the Center for Quantum Computing, which you can think of as our own R&D effort to build our own quantum hardware at Amazon. It's located at the campus of Caltech and led by Oscar Painter. And last but not least, the third pillar here is the Amazon Advanced Solutions Lab. That is our customer-facing team that works directly with our partners and customers in better understanding quantum computing and how it may ultimately affect industry, and that's the team that I lead. Okay, so let's step through these in a bit more detail first. As I said earlier, on Amazon Braket, you have already today access to different modalities that in particular include trapped ions from IonQ, superconducting qubits from Rigetti and IQM. All of them you can program through the famous quantum circuit paradigm, but you can also access the analog Q-error machine, Aquila, with up to 256 qubits, and that's actually the device for which I'm going to show you some experiments later today. The second team, the Center for Quantum Computing, is, as I said, located at the campus of Caltech. So this is where we build our own chips, where we work towards fault-tolerant qubits. It's a larger effort led by Oscar Painter. Earlier this year, we shared with you, with the community, some details. The details you can find in this Nature paper, where we published on our first chip called Ocelot. Okay, now we're back. Okay, I'm going to spare you the glory details because of time constraints, and now dive deeper into the Amazon Advanced Solutions Lab. So historically, we started as the Quantum Solutions Lab with a strong focus on quantum computing. That's still certainly part of our core mission, but over time we opened our aperture towards classical optimization, towards AI, machine learning, because we learned that this is the way how we can sort of transparently assess where quantum computing is today, where the bar is for quantum computing today and possibly in the future. And so some of the solutions we have discovered over time working with our industry partners are listed here at the bottom. These are some of the hardest problems that we've seen in industry. Some examples are vehicle routing, flight scheduling, sports scheduling, workforce rostering, clinical trial enrollments, forecasting, and portfolio optimization. And portfolio optimization is one of the examples that I'm going to use today in our collaboration with JP Chase. I'm going to give you a little bit of a flavor what portfolio optimization looks like, why it is actually hard, and how we can solve a simple version of portfolio optimization today on neutral atom devices. So we like to publish. Here are a few examples. We've actually worked with your neighbors, with BMW on a very interesting problem, robot motion planning. We've solved this problem both classically and with a sort of new quantum algorithm. We've worked with Fidelity on explainable AI. You can frame this as an optimization problem and discover compact Boolean formulas. We've worked with Goldman Sachs on essentially what it takes to put portfolio optimization on quantum computers. So we did an end-to-end resource analysis for that problem. And together with JP Chase, we've published a series of papers that evolve around the maximum independent set problem. The maximum independent set problem can actually also describe risk diversification and portfolio selection problems, and that was the interest from the JP Chase team. Okay. What is the challenge that customers such as JP Chase, but also others, face today? Well, they face some real-world optimization problems that typically involve large scales, so meaning many variables. So typically, if you think of portfolio optimization in the real world, that means thousands or tens of thousands of assets. These problems are typically heavily constrained. Typical constraints are budget constraints, cardinality constraints, sector constraints, risk-related constraints, etc., etc. And these problems have to be solved under stringent time and quality requirements. So that's the kind of core challenge, and these teams, they're interested if potentially quantum computing could help us with these challenges, maybe in the long run with fault-tolerant devices, but also with an eye on near-term quantum devices. Obviously being aware of the fact that we're still dealing with small scales, maybe hundreds of qubits. We have to deal with hardware noise and other imperfections, and typically constraints, at least in the standard approach, constraints can only be folded into your objective, into your Hamiltonian, via so-called penalty terms. So that was the challenge, and then something when we started this collaboration in 2022, something very interesting happened. So a science paper appeared coming out of the group of Misha Looking from Harvard University, MIT, and QEra, and they reported on a quantum speedup with up to 289 qubits, not just for some contrived mathematical problem, but actually for the maximum independent set problem. The core figure, the core result is summarized here. It's a bit of a mouthful, but essentially what you see here is the PMIS. That's your success rate to find the maximum independent set, so the optimal solution in one algorithmic shot, as a function of the hardness parameter. I'm going to define this in detail later, but essentially it tells you how hard a given problem instance is. And the upshot is that the red curve coming from the quantum experiment is above the blue curve coming from classical simulated annealing, and this is what led them to report on a quantum speedup, because your success rate, according to these results, is higher with the quantum device than it is with classical simulated annealing. Now that was an interesting result, and that prompted us to look more closely into the maximum independent set problem, knowing that it can find applications, in particular in finance. And so we went on a sort of scientific journey up to now that has resulted in these 4 papers. By the way, they all come with GitHub repos. The entire code is public source. So if you look into the archive, they all have links to the corresponding GitHub repos. So what do we do here in a nutshell? So in this first paper, we studied the hardness of the maximum independent set problem, in particular on unit disk graphs. Why? Because this is the type of instance that you can realize natively with Rydberg devices, meaning without overhead. And we sort of pinpointed how hard this problem really is. So if you think of time to solution in 2 to the alpha n, we pinpointed what alpha is using state-of-the-art classical devices, therefore defining what the bar is for quantum computers to beat. We then developed a decomposition pipeline for large-scale portfolio optimization problems. So using techniques from random matrix theory and community detection, we found that you should better use the structure that you typically find in real-world problems. So rather than throwing the initial instance, trying to fold it onto your quantum computer, use clever classical techniques that exploit the structure in these problems. And it turns out, if you look at typical S&P 500 data or Russell 3000 data, they have a lot of structure. So you can break down these problems into small sub-problems. Typically, you win by about 80%, and then you can solve the smaller sub-problems in parallel. And obviously, you have brought this whole problem closer to quantum hardware, because now, instead of 1,000 variables, you're dealing with 200 variables at maximum. In the third paper, we developed an end-to-end compilation toolkit. So you give me a generic problem. I translate it into a problem that is compatible with the connectivity constraints of Rydberg devices. And last but not least, we developed this Q-Redomis algorithm, a quantum-informed reduction algorithm. And that is what I will focus on today, because it sort of includes a lot of the lessons learned from the previous 3 papers. So this is what it looks like. It's a 3-tiered framework with an application layer, an algorithm layer, and a hardware layer. On the topmost application layer, what you see is, so typically your problem will be defined in terms of classical parameters. This could be expected returns, the correlation matrix that models risk, and a threshold parameter. You can use these parameters to construct what is called an asset or market graph. When you solve for the maximum independent set problem on this graph, it gives you a diversified portfolio. And this diversified portfolio could feed into a larger portfolio pipeline where you, within this diversified portfolio, you now allocate your capital within this portfolio, and that makes then an end-to-end portfolio optimization pipeline. So here we focused on how to solve this MIS problem on such an asset graph, but could be actually a generic graph, with quantum tools. And what we came up is with a hybrid algorithm that uses classical reduction techniques. And they are interesting because A, they are exact, so provably optimal, and B, they run in linear time. That's hard to find, so you better make use of it. And that's what we did. So we try to exploit this classical reduction techniques as much as possible. But whenever it gets blocked, it will query a quantum computer, and the quantum computer will tell it what are nodes that have statistically a high or low likelihood to be in the set. And that's what we refer to as frozen vertices or sample persistence. Now, these histograms you could essentially get with any quantum device, so using, for example, QAA on a quantum circuit. But given that Rydberg atom arrays can natively solve the MIS problem on unit disk arrays, we focused on these and built an end-to-end pipeline that involves schedule design, embedding. It defines an AHS, analog Hamiltonian simulation program, runs that on the quantum computer, does some post-processing, and with that feeds information into this larger hybrid algorithm. Okay, so now I'm going to try to step through these different layers, but sort of that will be the larger framework that sits behind it. So first, I mentioned already the MIS. So let's do the basics. What is the MIS? The MIS is essentially you're given a graph. So this is an NP-hard problem. You're given a graph, and you want to color as many nodes as possible, but you're not allowed to color adjacent nodes. So for this small toy graph, one example, MIS is colored here. So the MIS size is 3. The MIS problem is interesting for 2 reasons. First off, if you can solve the MIS problem, then you also have a solver for the maximum click and the minimum vertex cover problem, because they are dual to the maximum independent set problem. And secondly, it finds applications in map labeling, network design, vehicle routing, quantitative finance. So for example, if you open up Google Maps and it has to decide which items to label, it's essentially the maximum independent set problem. But it also is interesting for JP Morgan Chase and other banks, because they face a big computational problem, and that is portfolio selection, that I hope you will see when the monitor is coming back. Here it is. Portfolio selection. So the problem is you're given a large universe of assets, and we are tasked to find the largest set of uncorrelated assets. So now every node represents an asset, say Amazon stock, Microsoft stock, Google stock, and edges correspond to correlations between these assets above a certain threshold. So if you solve the MIS, it will tell you, okay, the largest diversified portfolio that you can find here is, for example, the basket that consists of assets A, C, and G. And it turns out that this problem can be solved with Rydberg quantum devices. So what are Rydberg quantum devices? So you have neutral atoms. So let's talk a little bit about physics now. You have neutral atoms trapped in ultra-high vacuum with optical tweezers. They interact via strong Rydberg interactions. Obviously, these interactions decay at some point, and that's sort of depicted here by drawing a blockade radius around every atom. And so whenever these are sufficiently close within the blockade radius, you draw an edge. And so that means that this is how you can see that you can create certain types of graphs, so-called geometric graphs, without overhead natively with these devices, because you can actually use these optical tweezers to essentially place these atoms at arbitrary positions. The system is described by a coherent many-body Hamiltonian. So you have a Rabi drive term here, you have a detuning term here, and you have the coherent atom-atom interactions. And interestingly, if you look at this Hamiltonian through the lens of quantum optimization, essentially what you have is a cost term. It's easy to see that this cost term describes the maximum independent set problem. And you have a coherent driver that allows you to couple different solutions to this maximum independent set problem, to the cost Hamiltonian. And so this is how you can use sort of annealing techniques to solve the MIS problem with these Rydberg devices. This is what it looks like in the original Harvard experiment. It is the end-to-end pipeline. So you can encode the problem, for example, so you place now atoms in the 2D plane. You tune your Rydberg radius such that you get nearest neighbor and next nearest neighbor interactions. So it's not a planar graph, but it gives rise to this sort of union check type pattern. You leave some sides open. That is why it's a random union check graph. So that means you can sort of generate many of these instances and gather statistics. Once you have placed these atoms at these positions, you make them subject to coherent, programmable quantum evolution that you can dial in by defining a schedule for the Rabi frequency, for the detuning frequency, and for the laser phase. So you have a lot of control over this coherent evolution. With Rydberg interactions on, you can optimize these parameters in a closed loop, and at the end of the day, you take a measurement, and you will find that some atoms are in the excited state and some atoms are in the ground state. The ones that are in the excited state are the ones that are selected for the maximum independent set problems. So coming back to our use case, this would be the assets that you want to invest in within your diversified portfolio. So coming back to the results, these were the original Harvard results in case they want to show up. So it turns out that you can analyze the performance. That's the probability to find the MIS in a single shot. And the quantum speedup that was reported shows up here as a more benign parameter in the exponent. So you find that the success probability is heavily determined by the hardness parameter. So now I'm telling you what the hardness parameter is. The hardness parameter is essentially the ratio of first excited states, the number of first excited states versus the number of ground states. So if you have if you have a large sea of first excited states and just a small number of ground states, then it's easily to get trapped in an excited state and not find the ground state. That makes the problem hard. And so what was shown is that that this exponent here is smaller for the quantum device, and this is why quantum speedup was reported. We looked at this problem very carefully and looked at this problem, if it shows up. Again, with the simulated annealing algorithm that Harvard used. This is shown here in green. And in red is our simulated annealing algorithm. It's better, and the quantum speedup is gone. But the details you find here in this algorithm, archive paper, sorry. I don't want to focus on the details, but what I want to focus on here is very fundamental, and that is that the performance is actually suppressed exponentially in the hardness parameter. And that holds for the quantum algorithm, for the classical algorithm, and in fact for any Markov chain-based type of algorithm. So it's a very fundamental limitation. And sort of that prompted us to look more carefully again at this problem. But so what have we seen so far? Quick summary. So you can solve the maximum independent set problem with Rydberg devices. On unit disk graphs, this is what a solution looks like, and we saw that the performance is suppressed exponentially in this hardness parameters, and it does so actually for a large class of devices. Okay, so this is a very fundamental problem, and it actually it made us go back to the basics. What are the basics? The basics here is any click can host at most one excitation, one selected node. That's a very fundamental property of the maximum independent set problem. A click is a subgraph of the graph that is fully connected. And the key idea is to identify or come up with the notion of so-called corner nodes. So these corner nodes, they will allow us to sort of reduce the easy degrees of freedom of the problem that you wouldn't, it would be a waste to throw them on a quantum computer, so let's get rid of them with a simple, actually exact classical algorithm, and then have the quantum computer focus on what is called the hard kernel or the hard core of the problem. So what is a corner node? A corner node is a node that has full connectivity within the host click. So this is a 3-click. You see node 11 is, I hope you can see node 11. Node 11 is a node that is connected within its host click a 3-click, 10, 11, 12, but it doesn't have outside connections, no outside world connections. Node number 7 could be a corner node. It has full connectivity. It's connected to all other nodes within this click of 3, 4, 5, 6, 7. But it also has connections to the outside world, number 10, and that makes it, disqualifies it for a corner node. So what we're going to play now is, okay, now it went ahead, sorry. Bear with me. We're going to play Pac-Man. We're going to play Pac-Man because we're going to remove these corner nodes step by step. Okay, node number 1 is an isolated node. Do we want to add it to our basket? Yes, for sure. Okay, let's add it, let's get rid of it. Let's look at the click defined by nodes 2 and 3. We know at most one of them can be selected. Which one do we want to select? What do you think? Do you think node number 2 or node number 3? If we select node number 3, it will disallow us down the road to select any of the nodes here, 4, 5, 6, 7. So we better take what is the corner node, node number 2, remove node number 3, and move on. Again, a click of size 2, 8, and 6. What do? Well, we do it in a minimal invasive way. We select node number 8 and move on. Same here, 9, 10. We wouldn't want to select node number 10 because then down the road we couldn't select 11 and 12, so we better take node number 9. The same here. Node number 3 is now isolated, so for sure we want to add it. Now we have a click, we could take any of them, we select node number 4 and we have solved the problem entirely. No quantum computer needed, linear time, and it's exact. So we have fully reduced the problem by a linear time algorithm that is optimal. So we will assess the reduction factor of such an input graph. It turns out the reduction factor of this algorithm is 100%. We have gone from the original input problem to an empty zero problem, and we are done. This is exact by a simple cut and paste reasoning. So you give me a click. We opt to select this node number V, which is a corner node. Clearly, it would be suboptimal to select no node in this click, so we want to select this node. Obviously, there could be other MIS solutions involving, for example, this node, this node, this node, but we can just cut it, paste it, sort of move it around to our corner node without incurring any violations and keeping the size the same. So we have applied this algorithm to real-world instances with roughly 10 nodes to 20,000 nodes. So these are sort of well-known benchmark instances from social network graphs with up to 20,000 nodes. And it turns out, because they have a lot of structure, they can be heavily reduced, typically by 90% or more. You see that some of these instances can be fully reduced, 100%, so the kernel is empty. And, but one very striking result I want to share with you, if you take the original graph, PubMed, 20,000 nodes, if you take standard embedding techniques that would cost you tens of millions of qubits to solve it with standard techniques, we propose to first run reduction, and it gives you, instead of the 20,000 nodes, it gives you a problem with 16 nodes that you can then solve. That's the hard kernel of the problem. Yeah, so we've heavily reduced the problem size, making no approximation whatsoever, and all of that takes less than a second on my laptop. So here's the runtime in MIS, and it scales linear in time. Okay, so what have we learned? Classical reduction technique is a powerful tool for the maximum independent set problem. You can actually generalize it to the maximum weight independent set problem. It is exact. It is very fast because it runs in linear time. So we better want to make use of it. And so that is what inspired us to embed that sort of technique within the Q-Redomus algorithm. So we use that as much as possible. At some point, it gets blocked because it doesn't find any corner nodes anymore. And at that point, we query a quantum computer to propose nodes that are likely in the set. And then, then it's an iterative cycle. It goes back and forth till you have solved the full problem. And that is what essentially makes this central layer in the algorithm. Here's the pseudocode. It has 3 main modules. First, we apply classical reduction on the original graph. It gives you a kernel graph. You then run. We store some metadata. You then on the reduced graph, you use, for example, a quantum solver. It will give you candidate-independent sets. With these independent sets, I can build out statistics and see what nodes are likely to be in the set or unlikely in the set. And with that information, I can remove a little bit of this kernel and then make it again accessible to a classical reducer, and then we restart in a recursive scheme. So this is what we use for the statistics. Here's a simple toy example. You see it has 2 MIS solutions, 2 and 3. Obviously, it's easier if you can see it. 2 and 3, 3 and 4. So what you see is node number 3, for sort of obvious reasons, is always in the set. So it's what we call a frozen in set. And then node number 1 is never in the set. So it's a frozen out node, and 2 and 4 have a roughly 50% likelihood. So you can now see what are the frozen degrees of freedom in the problem. Either you remove node number 3, and you're left with 2 and 4, or you remove node number 1, and you're left again with a simpler problem. Both strategies we have implemented. Here's an example for a problem that is so hard, hardness of 1,400 roughly, that the likelihood to find the MIS with a quantum annealer, even if it's tuned and optimized, is 0%. So what we do is we first apply classical reduction. It already removes 100 nodes. So instead of having to solve a problem with 137 nodes, we now have to solve this problem with 37 nodes. This is the hard core of the problem. Now we query a quantum computer, and it tells us that this node has a high likelihood to be in the set. So we add it to the set, we remove its neighbors, and with that we have created a new corner node, this one. And from that on, our classical reduction can play Pac-Man again, and we are done. And we have solved the MIS. So with 2 rounds of classical reduction and 1 query to the quantum computer. Importantly, the quantum computer never saw the original problem with 137 nodes. It only saw the reduced problem with 37 nodes, not making a single approximation. We've done this for several instances. You see, these are quantum annealing results. You see, as the hardness increases, essentially you fail. You have 0% success rates. With Eurythmus, you stay at 100% simply because classical reduction is so powerful. For a larger testbed that scans essentially 4 orders of magnitude, you see ultimately you hit the exponential suppression for quantum annealing results, and your success rate essentially goes to 0. With Eurythmus, if you involve reduction, you stay essentially up here, always above 90% success rate. One last important message. So we have done this with Rydberg atom devices, but the technique is hardware agnostic, and that is because essentially what you have to do is you have to unblock reduction. You solve the MIS problem that can be written as such. So it's a Cubo problem, or in other words, an Ising Hamiltonian. You can prepare low energy states as we did using Rydberg annealers, but obviously you could also do this on circuit-based machines using, for example, QAOA. So the impact, we believe, goes beyond Rydberg devices. And so with that, let me wrap up. I tried to introduce, whenever you were able to see the slides, I tried to introduce a quantum-informed Eurythmus algorithm, and where we heavily use on classical kernelization, that is used in tandem with a quantum computer as a co-processor. We've done successful experiments with up to 231 qubits on the QEra device, Aquila, in the cloud on Amazon Braket. And in the future, we hope to see more experiments on other devices. And with that, I'd like to thank you. Thanks.